welcome to one of our biggest Science Week events. Before we get started, I would like to acknowledge the country in which all of our Swinburne campuses are located on. And I think in Science Week, this is such an important thing that we do. Remember that a lot of our first knowledges come from the Indigenous peoples of Australia. And I myself am an astronomer, so I study the universe. And what I think is really beautiful is when we trace back some of those unique Indigenous knowledges to the sciences that we study today. So we pay our respects to the elders past, present and emerging, and really acknowledge the Wiradjuri people of the East Kulin Nation for the country that we're on today. So first of all, give yourselves a round of applause for coming out for Science Week. Excellent. This is that week in Australia where we get to celebrate everything that is science. It's that time where you, as the audience, get to step outside of your comfort zone and come and learn something new and interesting and exciting. And this is just the first step. We take science very seriously here at Swinburne. We have some incredible things that we do, and we're so excited to share just a snippet of them with you today. It doesn't stop here today, though. Throughout the entire week at Swinburne, we've got a few different exciting events for you. So I should introduce myself first. My name is Dr. Sara Webb, and I'm one of the scientists here at Swinburne. As I said, I'm an astronomer, so I study the universe. I'm extremely excited this week to not only be an astronomer, but be your Science Week ambassador, which means that over on social media and throughout a few different other events, we'll hopefully share the wonders of science. So we have one other event we would love to encourage you to attend, which is on Monday night at 6 p.m. This is a pizza and panel event. We like rhyming, at least I do, when coming up with titles. You will get to hear from scientists across our university in a range of different fields that will hopefully answer your breaking questions, like when will the universe end, what is a black hole, will machine learning and AI actually take over the world, the breaking questions you have on your mind. But they'll do it in a fun way that really encourages interaction with you and the questions that you have. And then afterwards, we will celebrate with some pizza. And who doesn't like pizza? So this is an all-ages event. It's open to anybody. So please take a photo of the QR code and sign up if you're interested. And we hope to see you there as well. But to get started tonight, before I hand over to Professor Alan Duffy and Professor Matthew Bales, I wanted to get you a little bit excited about science that we've brought from space back down to Earth. So one of the programs that we run here at Swinburne is we send payloads to the International Space Station every single year and have been doing it since 2017. What's really exciting, though, is in the past few years, we've figured out a way to not only send samples, but get them back so we can share them with you. So we have a specialty kit that we're going to hand out to some lucky people in the audience. We have 4 to hand out now and 4 to hand out later. So if you ask an excellent question towards the end, you might be lucky enough to win. But let's hand them out to our first winner. Who is it going to be? The lovely astronaut right there. Give her a round of applause. And we've got someone at the back. Give them a round of applause. And 2 more. Who's it going to be, Diana? Who's it going to be? Give them a round of applause. And one final kit. So if you're lucky enough, wonderful. Give them a round of applause. Excellent work. So you might have noticed these people were chosen because they look like they might be our future scientists of Australia. So what you've got inside your kit and what you guys can still win towards the end of the night is space seeds that we sent up last year, and they will grow. You have to promise me not to eat them because they have been in space and you don't know what has happened to them up there, if anything's changed, but you can grow them in your garden, which is pretty amazing. And we've got a full experiment in there, so you can do a control experiment, tell me if they've changed. There's a QR code for you to actually email me your results and help us do science here at Swinburne. So, enough of that fun. Hopefully I've riled you up. Are you all excited for tonight's event? Excellent. Yeah. I would like to introduce Professor Alan Duffy, our Pro Vice Chancellor of Flagship Initiatives, to be our MC tonight.
Thank you so much, Sarah, and thank you all so much for coming out this evening. I am, as was mentioned, a Pro Vice Chancellor of Flagship Initiatives. That means I bring together multidisciplinary teams across multiple organizations, hopefully raising multiple millions of dollars, to my boss there, to solve the most pressing challenges of our time. We have commenced flagships in supply chain decarbonization. We're trying to create green steel. We have new healthcare and medtech innovations coming with partnerships with St. Vincent's. At Swinburne, we work across domains because we know the solutions lie through collaboration. There is no silo in physics or engineering or chemistry or astronomy, but the science and the solution lies within. It is a collaborative approach, and that is what is so wonderful at Swinburne. Similar to Sara, I am by background an astronomer. I'm a computational astrophysicist. So that means that I create baby universes on supercomputers and try to understand how galaxies like our own Milky Way form within giant clouds of dark matter. I then try and find that dark matter as a chief investigator in the SABRE experiment, a 10-ton detector, which is sitting in our labs in our Wantirna campus, a project led by University of Melbourne's Professor Elisabetta Barberio. Very soon, I hope, because my team really want that space back, it will go to the bottom of an active gold mine in Stawell, Victoria, and there in the darkness, for the next 5 years, we will be looking for this dark matter. However, that is not the subject of tonight's conversation, so you can ask questions maybe of me afterwards, because this is a night all about Matthew Bales and his science. So let me just give you a little bit of background to Matthew. So he founded the Centre for Astrophysics and Supercomputing here at Swinburne in 1998, and rapidly became world-renowned for its groundbreaking research. Matthew's work was specialising on pulsars and fast radio bursts. I don't need to explain that. He's going to do a better job than I in a minute. But it was rather his broader leadership of both CAS and beyond that elevated all of us, astronomers here at Swinburne, but also nationally and beyond. In 2016, he became the director for the Australian Research Council Centre of Excellence for Gravitational Wave Discovery, known as OSGRAV, mercifully, a little easier to say. That's a $35 million program, 7 years he was entrusted with, to advance our understanding of gravitational waves. And he did such a good job that he was given another 7 years just now and $35 million to continue the research. Clearly not good enough to solve all of the mysteries, but good enough to entrust again. So could you please give a rousing round of applause for Matthew Bales, for those who Oh, no, I'm going to say more about him. I just want to applaud that. That's groundbreaking. Oh, it doesn't. Oh, there's more. All right. Last year, Matthew was awarded the Shaw Prize. This is known as the Nobel Prize, at least for his work, along with his collaborators, Duncan Larmour and Moira McLaughlin, for their work in discovering fast radio bursts. Something exploded 1 billion light years away, in the blink of an eye, releasing as much energy as the entire sun's output for a century. And we don't know what it is still. So, another award is coming, I suspect, for him when he explains what it was. Centres of Excellence, Shaw Prizes, accolades galore, but I know his proudest achievement is in 2014, when he hired me. Right? Okay, that is it for me. Could you please give a massive round of applause for Matthew Bales?
Thanks very much for the introduction. Today we're going to be using a brand new tool that's been created here at Swinburne and by some of our alumni called OSGRAV's Virtual Universe. And it gives us an opportunity to fly around the virtual universe and teach people about space and how physics works. And I hope it goes out without a technical hitch. The title of the talk is A Virtual Tour of Einstein's Universe. We're very familiar with the solar system and the Earth and the Sun, but I'm going to be taking you to a very extreme place where black holes and neutron stars inhabit some of the darkest reaches of the universe. And we're going to start by an object that was very dear to me when I was 6 years of age. Mankind was about to land on the moon, and the whole of Australia was gripped by kind of moon landing mania, including Matthew Bales, who had a little lunar rover, and I used to fly up around the lounge room and do delicate landings on the surface of the moon. And in South Australia, where I was growing up, we actually got a school holiday so that we could watch the moon landing. And my family had bought its first ever television set, which was really exciting, because we would watch Disneyland. Our parents made the claim that the television would only be on for half an hour a day, and soon that was blown away, partly because my father liked watching Homicide, great Australian drama. But we got sent home and we got to watch the moon landing, and I still remember it to this day. And I think it excited me about space, and fortunately I've been able to make a career out of it. So I want to explain to you, the public, who provided most of that $70 million for our Centre of Excellence, what we do with it and how we understand our understanding of the universe. And we're going to start by recreating a very important observation, which was Apollo 8 was orbiting the moon, and as they went around the moon, they saw the Earth rise. And we're going to recreate that here. And if you look in the middle of your screen, we're going to process time. And if you look really carefully, you'll see the Earth appearing there. It's the thing labelled Earth. We'll just take it out and you want to take a snap. So in this package, we get to be able to recreate these iconic moments in history. And when they took a photo of the Earth, and it was just in the blackness of space, we've got Jupiter there. It's not really that big, but if I make it the real size, you can't see it. The Earth is really that big, and it's up against the Milky Way galaxy, which is that dust lane. And our galaxy is like a pancake full of stars, but there's been so many cycles of star formation that dust has been erupted into the universe and it absorbs light, and we get that big black strip, which is the Milky Way galaxy. So if we go to our Earth, we'll find Australia soon. Toss it around here. It's a bit dark. Luckily you've got the lights on. So let's fly in. Melbourne is where my mouse is. And you can see Sydney, Adelaide. One of these dots is Alice Springs, where I was born back in 1963. But we have the power within us to cycle around the Earth and see how it looks at night, but also when the sun gets into the right place, what it looks like during the day. Now, the ancient people used the night sky as a way of telling what season was approaching. When certain stars appeared in the night sky, and we can pull out here, when certain stars came up, when the first night came, you could tell when winter was going to occur and when summer was occur. And most of the stars just look the same every night and never change. But the planets appeared to change. And the Greeks called the planets the wanderers, and we're going to see how they wander. So I'm going to speed up time so fast that the Earth, you can see we've got about a day per second happening. And if you look at Saturn here, and its motion, it's appearing to drift to the right. And the Greeks documented how the planets moved in the sky, but the stars didn't. So there's Mars drifting by. That big yellow ball's called the Sun. There we've got Venus, and we can actually highlight them. And the Greeks came up with this weird concept called epicycles, because they noticed that the planets appeared to go in one direction on the sky, and then at certain times of year they would sort of do a U-turn and go back, and then keep on their march again. And this was very confusing, because the planets, although they were travelling across the sky, they weren't doing it in a particularly linear way. And so it was very difficult to understand that. Fortunately, Copernicus came along in the 1500s, and he realized that if the Earth went around the Sun and the planets went around the Sun, he could explain their positions. So if I now zoom out a little bit from the Earth and speed up time, and you can see our moon. But you can also see the other planets going around in what are really quite bizarre patterns. What Copernicus realized, if we changed our reference frame to the Sun, and we did the same thing, the patterns that the planets would trace around in 3D space, if you like, was much more sensible. And he thought that they were all going around in circular orbits around the Sun. He didn't have the accuracy of measurement to be able to do much better than that. We can see that if we're orbiting the Sun, the planets appear to be going around in quite easy to comprehend motions. And so Copernicus was so terrified that his discovery that maybe the Earth wasn't the centre of the universe, that he only published his work in the year of his death. So he was virtually on his deathbed when he revealed what he thought to be the truth. We didn't make a lot of progress for some years after his discovery, although his book was published, until Kepler, who was a great Polish astronomer, went to work with the observational astronomer of his day, a guy called Tycho Brahe. And Tycho Brahe had lost his nose in a duel, but he was really good at looking at the stars. And he didn't have a telescope. He had these strange devices that could work out the positions of stars very accurately just by pointing effectively a rod at them with like a crosshair. And he documented very carefully where the positions of the planets were every night. And Kepler in about 1610 managed to come up with trajectories for the planets that explained their motions. So he was obsessed by geometrical shapes, and he realized that an ellipse, which is what a circle looks like if you see it slightly edge on, could explain the motions of the planets. And the speed at which the planets went around the Sun depended on which phase of their orbit they were at. So we can see the first planet there, Mercury, is travelling around the Sun. It's actually in what we call an elliptical orbit, and it goes faster when it's near the Sun than when it's further away. And that was Kepler's first law, was that they travel in ellipses. The second law was they travel faster when they're near the Sun than when they're further away. And his third law accurately described how the time it took to go around the Sun depended on the distance from the Sun. About the same time, Galileo was the first person to point a telescope at the planets. And he looked at Jupiter, which is what we're going to do here. Whoops, that's that one. We'll come back there later. So he looked at Jupiter, and what he noticed was that it had 4 moons. So imagine that, he's the first person to grab a telescope and point it at the sky, and when he looked at Jupiter, he saw that it was surrounded by these 4 dots. And he soon realized that the next night they'd changed their position. And he did these beautiful diagrams in his notebook about where they were. And he realized that Jupiter must have moons. You know, we can speed up the passage of time. I'm going to turn off the labels. Hopefully can you see the moons? You can see the moons going around Jupiter. And he noticed that they were changing their positions. And he realized that if Jupiter had moons and the Earth had a moon, then maybe the Jupiter and Earth are more similar to each other than the Sun and Jupiter. And so he postulated that Copernicus was right, and that maybe the planets did go around the Sun. And this was a great breakthrough. And when he explained this to the people of his time, he was placed under house arrest for heresy. I think he was later forgiven by the Catholic Church some hundreds of years later. So, while we're in our virtual spaceship, we might visit some of these moons. They're quite fun. The little girl who got the prize, who was 3 years old, knows the names of the moons, which I suspect I don't. Embarrassing. So this is Callisto. This is Ganymede. This is the largest of the moons, I do know that. The next one is my favourite. It's called Io. And Io spins faster than the others. It's actually quite close to Jupiter. You can see Jupiter whizzing by there. And it's very volcanic. And the reason it's volcanic is it's so close to Jupiter that the tides of Jupiter cause it to get squashed and squeezed. And it's like one big sort of volcano made of lava. And in a future version of our program, maybe we'll show the volcanoes spewing out lava from the planet. We can look at what it would be like to look at Jupiter whilst we're orbiting Io. Slow time down a bit. It's quite picturesque. So this is what it would be like if you were orbiting Jupiter, Io, looking at Jupiter and flying past the moon of Io. If we speed up time a bit, you'll see the other moons in the distance flashing by. And then there's this planet, which I believe is Europa. Europa is thought that it might have liquid water underneath it. And we can fly in and see what that one's like. So we have 8 major planets that orbit the Sun. We're just going to do a little tour of them. Mercury, we're on the dark side here. The dark side of Mercury is incredibly cold because it doesn't have an atmosphere to keep it warm. And it actually takes 66 days for Mercury to spin around. And it only takes about 99 days to actually orbit the Sun. It does have quite good photographs of it, so we can show you what it looks like. It kind of looks a bit like the moon. And the reason is it's not heavy enough to keep its atmosphere. But on the sunny side, it's incredibly hot. And on the dark side, it's very cold. So if you could picture yourself right at the right spot, you could probably get 20 degrees. It would be quite nice. But since there's no atmosphere, it wouldn't be very nice to visit. Let's fly to Venus now. Venus is about the same mass of the Earth, but it's just a big cloudy carbon dioxide nightmare. So it's so hot because it traps all the heat. A lot of greenhouse gases, and it's many hundreds of degrees Celsius. It actually rains sulfuric acid. So any space probe we send to Venus only lasts a minute or two before it gets dissolved by the sulfuric acid rain. So it's certainly not the place you want to go to. The Earth we've already been to and are very familiar with it, but we've known that the Earth is actually round for centuries. And that's because a Greek scholar known as Eratosthenes noticed that at certain times of year, the sun, he read that at certain times of year, the sun would shine directly into a well in Alexandria. And he knew how far away Alexandria was away, and he also knew that day. And so he waited until that day to recur, and he measured what angle the sun was making with wells in his area, and he measured the circumference of the Earth. And actually got it pretty right. Mars is one of my favourites, partly because it has these extinct volcanoes that we can see here now. The largest mountain in the solar system is actually Olympus Mons. We're going to fly into it now. It's 27 kilometres in altitude. And the reason it doesn't fall down is because the Martian gravity is only about 1/3 of what we have here on Earth. So it's easier to make a big mountain. It also doesn't have much erosion because the atmospheric pressure on Mars' surface is only a few percent of that of the Earth. So although it's very windy on Mars, there's not much material to erode things. So these ancient volcanoes can live for billions of years. You can also see the craters due to the impacts that Mars has experienced. And it also has these intriguing canyons. It'd be kind of fun to fly down them. Mars has some very interesting moons that teach us about gravity, which is the subject of this lecture. So if we go to Phobos, Phobos is not round, and that's because it's not big enough to make its mountains fall down. So the gravity on Phobos is very, very tiny, and it's only about 20 kilometers across. And so if we look at Mars from Phobos, it's actually only a few times the radius of Mars, and it orbits every few hours. And in fact, it orbits faster than Mars spins. So instead of rising in the east and setting in the west, it rises in the west and sets in the east. And you can get these beautiful vistas in our little simulation here of what it would be like to be orbiting Phobos whilst looking at Mars. There's another planet, Deimos, and again we can look at Mars. It's much further out and in a more stable orbit. We think that Phobos might eventually be destroyed by its close interactions. And you can see Phobos there orbiting Mars, and it will merge again there. We've already been to Jupiter, but we can visit Saturn, which is one of my favourite objects to look at with a telescope. Saturn has these amazing rings, and you can think of them as pulverized moons. And in space, if you're spinning, you tend to want to become a pancake, and it's only due to gravity that you get pulled inwards. But if you're spinning at just the right rate, you can get a long-lived structure, like the moons here of Saturn. So we can fly through the rings. When we look on the dark side of the rings, it's very difficult to see them. But the rings actually do cast a shadow on Saturn. We just normally can't see it because we're on the Earth, which is very near the Sun. So we're basically aligned with the light source. But in this program, you can have a lot of fun flying around the universe. There's only one major moon of Saturn. It's called Titan. And you can get a really nice view of Saturn whilst orbiting Titan. And if we wait long enough, we'll get to be able to see it from the sunny side. So it's right there in the middle. And there you've got the beautiful rings of Saturn. And the Saturn casts a shadow on its rings. There's a couple of more boring planets. This is Uranus and Neptune. These are the gas giants, so they're very large compared to the Earth, but they're very far away, and because they're so far from the Sun, they're rather cold. So we've learned that Copernicus discovered that the Earth wasn't at the centre of the solar system, that Kepler had his laws of planetary motion that appeared to work very well, and that Galileo had discovered the moons of Jupiter displacing the Earth from the centre of the solar system. But we didn't really make much more progress on our understanding of gravity until the time of Newton, who was lucky enough to have a pandemic breakout in 1666 in London. And he was sent away from Cambridge to his home, and there he developed his universal theory of gravitation and also differential and integral calculus, all in 2 years. I'm sorry, Pascal, when I was sent away for 2 years, I didn't quite get there. So we're going to go back to the rest of our talk now and learn a bit about, first of all, Kepler's laws. And Kepler was the first person to connect mathematics to the trajectories of the planets. And in this program, we can actually trace out the path of a planet. And you can see that in this simulation, it's orbiting the Sun. It looks suspiciously like Mars. But Kepler's first law was that that path should be elliptical, and they should sweep out equal areas in equal time. That means they go slower there at aphelion than perihelion. And that there's a mathematical relationship which tells us how long it takes to go around the Sun, dependent only on the distance to what's called the 3/2 power, and a bunch of other stuff that Kepler didn't really understand, but Newton was able to show that this formula is correct. So Newton developed his universal theory of gravity, allegedly when an apple fell on his head. It was probably folklore. And he realized that if the only reason an object changed its trajectory was because it experienced a force, and there was a universal law of gravitation, the same force that explained how apples fell from trees could explain how cannonballs moved in the air and how the planets moved around the Sun. And so what we're going to do is show that if you have a projectile, which is something like a cannonball fired from a cannon, it'll actually trace out a parabola. So this y equals minus x squared formula, which you probably all learned at school if you're old, this traces out a nice parabola. And Newton was the first person to understand that the acceleration was just caused by the universal law of gravitation, and that the time that it took to go up and back down again was the same whether you were going straight up or whether you were kicked slightly to the side. And so he was the first person to use mathematics to be able to explain the trajectories of objects. And his universal law of gravitation was a triumph in our understanding of gravity. So what are the consequences of his law? First of all, the gravity that we're feeling on Earth, the gravitational law is the same on the Earth as it is everywhere else in the universe. And Kepler's laws using calculus could be described, Kepler's laws could be derived just from his universal law of gravitation, and the fact that the amount you accelerate depends on the force being applied and how heavy you are. And so we had a transformation of just wondering what the stars were doing to actually be able to predict where they were going. But we could also use those same laws to understand how apples fell from trees or cannonballs flew around the Earth. So people would ask Newton, well, why doesn't the moon fall down if it's subject to your law of gravitation? And so we can understand that by this package has a simulator in it, and I can take the moon and I can roll it out of my cannon so that it just falls down. And what we'll see is that the moon just falls into the Earth and disappears. There's actually a bug in the program. It sneaks out the bottom. We can then give the cannonball a slightly bigger trajectory, and it tries to get around the Earth, but it ends up in Russia somewhere. Better the Ukrainians would like something like that. You can get a little bit further if you give it a larger kick. If you give it too big a kick, you're in trouble because you reach what's called the escape velocity, and the moon will just fly off forever. Or if we manage to kick the moon at exactly the right speed, it falls by the exact amount that the Earth curves, and it ends up orbiting it forever. So I can turn on a little trail here, and you'll see that the moon is tracing out what's called a circular orbit. And this is how satellites orbit the Earth. You give them just the right speed, and they fall at the right amount to just go around forever. If you're above about 700 kilometres, you actually will go around forever. If you're below about 600, the atmospheric drag will be enough to slow you down, and eventually you'll crash back into the Earth. So this is how Einstein, that's coming later, This is how Newton explained the motion of the Earth around the Sun and why it didn't fall down. Unfortunately, this is how big the Moon really is. And a keen-eyed among you will be able to see there's a little dot here just going above the Earth at the moment. And, sorry, above the word Earth. That's actually how big the Moon is. And so it's about 1.3 light seconds away, or about 400,000 kilometres, and it takes about a month. If I make it a bit easier to see, I can leave a little trail there. So this is how the Moon travels around the Earth. And the Moon actually spins by one rotation in absolute space for every orbit of the Earth. And that's because it's what's called tidally locked. And there used to be a thing back in the 1960s and 70s called the Colgate ring of confidence. Who's old enough to remember the Colgate ring of confidence? I still use Colgate to this day. If you're an insecure female in a 1960s commercial, you could use Colgate and you would be surrounded by the Colgate ring of confidence. And when the instructor leant in to teach you how to fire a gun, which was kind of odd, you would not have to fear that your breath smelled. So it occurred to me when I saw this simulation that we had an uncanny resemblance to the Colgate ring of confidence. All right. So that was the 1600s. Newton had done a magnificent job at explaining the trajectories of the planets. And it was actually a few hundred years until our next bit of progress. And that was when a guy called Albert Einstein came along. And Albert realised that he wasn't really cut out for physics, and he took a job as a patent clerk. And he used to stare out the window and do these wonderful thought experiments. And he wondered if you were experiencing gravity because you were in an elevator that was at rest, could you tell the difference between that type of acceleration and acceleration in the rule of outer space? If you're accelerating at 9.8 meters a second, every second, so getting faster and faster, in outer space, you would feel a force that felt a bit like gravity, but it wasn't really gravity. And if you were in a box which was just on the Earth, this shouldn't be hanging up in the air, I'll get Carl to fix it later. If it was just sitting on the Earth, could you do an experiment that would be able to tell the difference between these two scenarios? And he said if there wasn't, there's a whole lot of mathematical consequences. And one of them was, maybe you also couldn't tell the difference between just floating in free space and being in free fall. We all know that astronauts don't feel gravity. So one of the consequences is if you were holding up two mirrors and firing a light between them, the light would move in your elevator and it would have to bend as it travelled around your object. Another thing that should occur is the clock should tick more slowly near strong gravity than away from it. If you took a ruler and you took it near strong gravity, it should shrink or expand if you're in deep outer space. And he also realised that if you compressed objects enough, not even light could escape. And so we have the concept of a black hole, and all you have to do is compress the Earth into something 9 millimeters in radius, and you could turn it into a black hole. That's kind of challenging. You and Alan Duffy. If you can get the Sun, if you could compress it into something 3 kilometers in radius, it would become a black hole. But Einstein thought these were just fictitious notions. Another thing he realised is that when two objects went past each other or around each other, they should give off a wave of gravity, in the same way that when two charged particles go past each other, they emit light. And so he postulated the existence of these things called gravitational waves, and the amplitude of the gravitational wave, this is how much you get squeezed by it that passes through you. He worked out for most things he knew about, it would have an amplitude of about 1 part in 10 to the 24, which is not very much. So if you had like a 1,000,000 kilometre ruler, it would shrink by less than the width of an atomic nucleus. So he thought that whilst these were an interesting mathematical construct, they actually had no part in the physical universe. And he died. It was really sad. In fact, he even tried to revoke his paper on gravitational waves, saying, I made a terrible mistake. They don't exist. and the referee of the paper rejected it. And so Einstein never published in that journal again. And the reason he rejected it was because he said, "You're right, Einstein, they do exist." And he was correct. So some of Einstein's predictions, we already talked about clocks ticking more slowly. So if I have a clock in my pocket, and I put it higher up in the Earth's gravitational field, it actually ticks faster than Earth's down here, which might not seem true, but it is. If you have an atomic clock, you can do this experiment and show that it actually ticks more quickly. That rulers should shrink, that light should bend around bodies, that any two bodies orbiting each other should give off these gravitational waves, and these gravitational waves take away energy and it causes the orbit to shrink. That black holes would emit no light, and then if you're a spinning object in a gravitational field, your spin axis will precess over the course of millions of years. And he also thought that gravity would travel at the speed of light. And so people started doing experiments to see whether he was correct. And it was already known at the time of Einstein in 1915 that the orbit of Mercury couldn't be explained by Newton's gravity alone. And what's called the elliptical perihelion of Mercury was changing its orientation with the Sun by an absolutely minuscule amount, which seems like you'd never go to measure it. Every 8,400 years, the ellipse would change its phase by 1 degree, which means that Mercury would move by less than its radius every orbit. And yet this was known about and was unexplained. So that was considered a test of relativity. So if we fly to the Sun, see how that would work. No pressure. So Mercury has its elliptical orbit, and every 8,400 years, which is about 35,000 rotations, this ellipse would change by 1 degree. And you would think you've got to measure that, but we have measured it, and it's amazingly true. The other thing that was realised was that light should bend around the Sun. But the problem is it's pretty hard to make measurements of stars behind the Sun when the Sun is shining. So if you wait, you can wait for a total lunar eclipse of the Sun. Hopefully I can do. And then all of a sudden you can see the stars and see that their positions has changed because the light has bent around them. And so in the expedition in 1919, Eddington did this and showed that indeed light was bending around the Sun. And in the 50s, they built atomic clocks so accurately that if you stuck one in an aeroplane and flew it above the Earth by about 10 kilometres and then brought it back down and compared it to a clock that had been left on the Earth, it had indeed ticked faster. Only by about 1 part in 10 million or so. But enough for us to be able to easily measure. So Einstein thought this was good, but gravitational waves were never going to be able to be detected because their effects were too weak and stars were too fuzzy. And in fact, it's the density of a star, how many kilograms per cubic metre, that actually tells you how quickly you can orbit it. And it turns out something like the Sun, even if you're at the Sun's radius and you're orbiting it, it would take you several hours to get around it. And the only thing that actually determines how fast you can go around something is the density. It's the square root of 1 over the density. And unfortunately, stars are usually hundreds of radii apart, so even if you get two stars like the Sun going around each other, the gravitational wave emission is such that you can't really measure it. If you go to something like Jupiter, its density is only 1.3 grams per cubic centimetre. That's not much good. Even the Earth is only 6 grams per cubic centimetre, so the minimum orbital period is about 90 minutes. And these just aren't good enough to be able to do experiments pertaining to gravitational waves. So it looked kind of hopeless. But how big is the Earth compared to the Sun? Well, we can do something fun. we can put the Earth above Saturn's rings, and then put the Earth in the the Sun in the background, and you can get an idea of how big the Earth is compared to the Sun. You can actually fit 1 million Earths in the Sun. And the Sun is about 300,000 times heavier than the mass of the Earth. Luckily for us, the Sun is not a very big star by galactic standards. There's a star called Rigel, which is in the Orion constellation, and it is about 20 times heavier than the Sun. And if we compare the Sun to Rigel, flying out, you can see that our Sun is kind of pathetic. Uh-oh, we're about to go through a blue supergiant. Hold on, we'll see. So there's these stars which are 20 times the mass of the Sun floating out there in the galaxy, and they're very, very bright. And they're actually about 80 times the radius of the Sun. They have a temperature something like 3 times heavier than the Sun, and the luminosity of these stars is about 100,000 times brighter than our Sun, so you wouldn't want to live anywhere near it. Unfortunately, they're burning the fuel so quickly, they're only going to live for about 10 million years, and then they're going to blow up. And when they blow up, they're going to leave something very special behind called a neutron star. And the neutron stars have basically removed all of the interatomic spacing between atoms and formed pure neutrons. And a cubic centimetre of a neutron star weighs as much as all of humanity. So they're kind of dense. And if you remember back a few slides, the speed at which you could orbit something depended on 1 over the square root of the density. So if you put every human into a cubic centimetre, it would weigh quite a bit. It would be great for doing experiments. So what's actually happening in the centres of stars? Shortly after the Big Bang, almost 75% of the universe was in hydrogen, about a quarter of it was in helium, but in the centres of these stars, hydrogen and helium are being burnt, and they're actually forming higher elements such as carbon or iron. And once you've formed iron, there's no more energy to be gained by merging iron with something else, so you tend to end up with an inert ball of iron in the centre of stars. When it becomes about the size of the Earth, it weighs about 500,000 Earths, and all the poor electrons and neutrons can no longer resist each other, and they become electrons and protons can no longer resist each other. They become a neutron, and the centre of the star collapses in what's called a supernova explosion. And the reason there's such an enormous release of energy is that normally an iron atom, if it was the size of a ping pong ball, the distance to the nearest ping pong ball would be 1 kilometre. And so there's all this empty space, which is usually just housing the electrons and keeping all of these atoms apart. That all gets compressed, and we end up with what's called a neutron star. But these were very hypothetical conjectures until the 1960s. So this is what a star looks like when it blows up. This is what's called the Crab Nebula on the left. It blew up in 1054 AD, and it was so bright it would cast a shadow at night time. The thing on the right is a little bit more boring. It's called a planetary nebula. That's what's going to happen when our Sun dies. It's going to leave behind a white dwarf in the centre here, and it'll just get this nice, beautiful lit gas via the light coming from the white dwarf, which eventually will fade away and be a brown or black dwarf. So we think we live in a galaxy a little bit like this one. This is about 100,000 light years across. There's about 400 billion stars in these galaxies. And we think we live about 2/3 of the way out from the centre of our galaxy. And our galaxy looks a little bit like this. It's a thin pancake that's sort of being compressed in one direction, but in the direction it's spinning, or perpendicular to the direction it's spinning, it actually is a big flat sheet. This is the centre of our galaxy. It has a big bar and spiral arms. And we think we're about 2/3 of the way up in one of the spiral arms, which is very flat. And when we see the Milky Way, it's because we're embedded in this thin sheet of stars. but a lot of the light gets blocked by the dust, so we get the nice dust lanes. This is what happens if you look at the sky with radio waves. So this is the centre of our galaxy. I really love this diagram. It's from Sara Webb, which is the South African Radio Astronomical Observatory. It was their first ever image that was released at the grand opening. And these things here are exploded stars. There's these weird kind of filament things. Right in the centre here, there's a supermassive black hole. And amazingly, this little guy here, this little dot with the big jets, that's actually a supermassive black hole in a galaxy far, far away, squirting out jets of material. And we can see that all in this image. So if you look at the galaxy with radio eyes instead of optical eyes, you get a very different picture of what's happening. The radio waves travel through the gas, they're not reflected by it, and you see these odd structures and exploded stars and things that are not what we used to. So this is the telescope that made that image. Swinburne is actually building some of the equipment for this. This is going to be part of the square kilometre array. They're going to add another 132 dishes to the 64 that already exist. This is the telescope I kind of grew up with, the iconic Parkes radio telescope. And it helped bring back those pictures from the moon that we saw when I was 6 years old. So there was a study going on back in the 60s, which was what are the quasars? So this is an image of a quasar or a radio galaxy, and this is our model of it. The idea is there's a black hole with accreting material. The material becomes magnetized and squirts out these jets. And if I was to fly out here and orient this the right way, you can see how I would explain this blob of material with jets. The distance here is about a million light years, something like 10 times the diameter of our galaxy. So there was a young woman called Jocelyn Bell back in 1967, and she was studying why it was that quasars scintillated. That means they twinkle. So if you look in the radio at these quasars, they actually change their brightness on very rapid timescales. And she and her advisor, Anthony Hewitt, built a radio telescope to look at the sky and record how it changed about every 100 milliseconds. And on the 6th of August 1967, remarkably, she looked at this thing that looked a bit like interference. This is when we used pen and paper to do our radio observation. And she noticed that something was causing the pen sharp to go up and down. This is time in this direction, and this is how bright it is in the other direction. And she could somehow tell the difference between this thing and this interference. And so one night she cranked up the chart recorder, and she saw that there were these blips occurring about every 1.33 seconds. And we're going to listen to what that sounded like. I'm going to type in this password. So we actually run an extension program for school children here at Swinburne, and I got them to do some audio recordings of pulsars from the Meerkat telescope, and Rebecca, Evie and Rudra in the front row there did it. I'm going to stick this loudspeaker near my microphone, and we're going to listen to a pulsar that rotates every 2 seconds, and I can just about do that. And every time it rotates, it sends out a burst of radio waves across the sky. Hope this is going to work. So if you're observing with the Meerkat telescope, every 2 seconds you get this burst of radio waves, and you can actually hear it, which we just did. However, there's more exciting pulsars. This one here spins about 2.5 times a second. I can't do that very well. Oops. is real data. You're actually listening to it. You can listen to the sky with radio waves. So that one's rotating 2.5 times a second. It's 20 kilometers across, and it's spinning 2.5 times a second, and it's got this beam of radiation. The reason it doesn't fly apart is it's just made of neutrons. But it's better. There's a very young pulsar called the Vela pulsar, which is only about 500 light years away, and it spins 11 times a second. And it's kind of loud. So remarkably, that guy there is spinning 11 times a second. That's because it's only about 10,000 years old. It's still spinning very rapidly. And then there's my favourite pulsars, which are called millisecond pulsars. That one spins 173 times a second, which is amazing. And we're going to learn briefly about how they come about and some of the things we can do. So this is what we think a pulsar looks like. It's made of neutrons. It has this beam. There's about 3,500 of them known. Over 500 have been discovered here at Swinburne. They're only about 3 times bigger than a black hole would be, and they're almost perfect clocks. So the rotation can be used as a clock. And once you have a clock in space, you can do experiments in gravity with them. We've already seen where they come from. And how big are they? Well, if you put a black hole, a neutron star, and a white dwarf, and the Earth together, this would be about the right size. A white dwarf is what happens when the star doesn't blow up and it retains being normal matter. These are where all the pulsars are in our galaxy, and the sun in this animation is right here in the middle of all these pulsars. And the reason there's so many there is they're easier to find if they're close. Back in the 1970s, there was a student doing his PhD, and he was the first person to use a computer to find pulsars. And when he did it, he found this one, which was called the binary pulsar. And the binary pulsar also travelled in elliptical orbit because of Newton's law of gravitation being universal. And it was going around another neutron star. And instead of them taking a year to go around each other, they actually went around each other every 8 hours. And this is the sort of speeds that you need in order to be able to see gravitational wave effects. And so he and his advisor, Joe Taylor, who happened to mark my PhD, were awarded the 1993 Nobel Prize in Physics because of discovering this object. So how do these objects form? Just quickly, you have a big star and a little star. The big star lives life fast, and dies young. It transfers matter onto its companion, and then it blows up. And when it blows up, most of the time it just gets away from its companion and it flies around the galaxy, and it's kind of boring. But if we're very lucky, it's bound by gravity to its companion, and it goes into one of these big elliptical orbits around its companion, and it takes about a year or two to go around. So how big are these systems? Well, this is how big our sun is, and this is the orbit of the neutron star going around its companion. So they're quite large. The neutron star would actually just be a point on this diagram if I did it to scale. It wouldn't be very interesting to look at. And so we've actually discovered 2 of these objects and studied them at Swinburne. This one goes around every 50 days. Eventually, the big star in that other diagram, sorry, that other slide, swells up and it transfers matter onto the neutron star. And when it's transferring the matter onto the neutron star, it gives off so much energy that it's equivalent to 100,000 nuclear wars per meter squared per second. That's how much energy is coming off when the material is flowing onto the neutron star. It forms this disk which makes it spin really, really quickly. And you end up with either a neutron star going around an inert star, which is called a white dwarf. This is a famous system discovered at Swinburne called the diamond planet. In this one, the pulsar and companion have a mass ratio of about 1,000 to 1. We think this is made of carbon, so we called it the diamond planet, and we've increased our number of hits. This whole system is so compressed, it would almost fit inside the sun. This is my favourite system. It's called 1909 minus 3744, which means it comes up 19 hours and 9 minutes after Aries, and it's 37 degrees south of the equator. In fact, it goes over Melbourne, yes. And we've been able to measure, use the clock, which is the pulsar in this system, to measure that the orbital period is 1.5334494774790 days, and the rotation period of the pulsar is 2.94, lots of digits, milliseconds. It's travelling around about 200 kilometres per second, and it's about 3,000 light years away. And what happens in this system is that it's actually very face-on. And because it's so face-on, when the light from the pulsar goes past the white dwarf, the measuring rods are shrunk, and it takes longer to get by than it otherwise would if Einstein's laws were not correct. So we measure when the pulse hits our telescope to an accuracy of about 100 nanoseconds, and then we can check that what is the shape of the orbit? Is it really an ellipse? And this system is so circular that the semi-major axis and semi-minor axis difference is only 4 microns, even though it's going around an orbit which is 569,000 kilometres. So it's one of the most perfect circles known in the universe. And the black line here is Einstein's prediction of how long it should take the pulse to reach us as a function of the phase of the orbit. And if you subtract the measurements, which are the black dots, from the curve, you get this. It's a perfect confirmation of Einstein's theory that measuring rods really do shrink when light is travelling past an object. Eventually, two stars, or sometimes they both form neutron stars, and you end up with something called a double neutron star. And if Einstein's correct, then because these things are giving off gravitational waves, the orbit should shrink by 3 millimetres in orbit, which doesn't sound like very much, especially when you think this thing's 20,000 light years away. And so every time they go around, the orbit shrinks by 3 millimetres. Luckily, that's cumulative, so it's 6 millimetres, then 9, then 12. And they take longer and longer to reach their point of closest approach. And so if you're really careful when you measure this long enough, you can infer that in a few 100 million years, the two neutron stars will be going around each other 1,000 times a second. So the orbital period will be 1 millisecond. And they'll give off a burst of gravitational waves that will radiate through the universe, and we should be able to detect the black hole that was formed. So the original binary pulsar was going around its companion every 8 hours, and if Einstein was right and gravitational waves were being emitted, you could predict when the neutron stars would get back to their point of closest approach and compare that with your measurements. And so the black line is Einstein's prediction. It's a pity he was dead. The black lines are the confirmation. And in about 1993, they awarded the Nobel Prize to Taylor and Pulse for discovering this object. But this was also the impetus to build something called LIGO, which was a gravitational wave detector. Let me just check how much time I have left. -4 minutes. There was 2 4-kilometre vacuum tubes, and if you fire a James Bond-style laser down here and recombine the light, you can see if gravitational waves have travelled through your apparatus. So this shows you it's real. I was on an advisory committee for LIGO, and on the 17th of August 2017, they measured how much gravitational power was in the system versus time. This is about 20 seconds. And you can see that there was a gravitational wave that got faster and faster. This is because the two neutron stars went around each other faster and faster and ended up ripping each other apart. 1.3 seconds later, we got a burst of gamma rays hitting the Earth. We looked in the sky, and there was a brand new object there, and that's what's called a kilonova. It's what people like Sarah spent her PhD looking for, and we could confirm some remarkable things. The first of that neutron stars converge, and that explains how we get elements like gold and titanium. So if you have a wedding ring on, that was probably once in a neutron star merger, and that the speed of gravity was almost identical to the speed of light, even though these objects have been travelling for 40 million years. So I have a lot more material, but I think we all need to break. So let me just flip over the rest of this and get to my conclusions. This shows what happens if clocks don't tick properly when you've got two neutron stars going apart. The delay, because of the clock ticking more slowly when the two neutron stars are closer, is predicted to be 384 microseconds, and that's exactly what we've seen from two neutron stars. We've got another double neutron star called the double pulsar, and it shrinks by 2.71 millimeters in orbit. And the red is Einstein's prediction, and the white is the measurements we made here at Swinburne. The light from these two neutron stars actually bends around each other, and we can see light bending in the system. And because the light is blocked by one neutron star as it goes past another, you actually get eclipses. And you can use the orientation of, or the shape of these eclipses to work out where the spin axis is pointing. And you can show that because of relativity, the spin axis is precessing every 80 years. We're also looking for supermassive black holes. And if supermassive black holes are radiating gravitational waves through the universe, we can use an array of these millisecond pulsars to look for correlated signals. And we should get a special curve called the Ellings and Downs curve. So I had some school kids come in last summer, and we were looking to confirm that what other groups have done with other telescopes would give rise to what's called the Ellings and Downs curve. And there we are with our first plot to show that we're getting roughly the same signal. Finally, we detected a neutron star in this globular cluster. These are these balls of stars which have a whole lot of neutron stars in the middle. There's collisions that take place in the centre of these globular clusters, and we discovered a very rapidly spinning pulsar in what's called a highly eccentric orbit. And Scarlett here, for a work experience program, made me this little animation of what would happen if you had a millisecond pulsar with a white dwarf companion come across a black hole. And it's kind of fun. They interact. The neutron star almost gets away, but the gravity is too much and pulls it back towards the black hole and the white dwarf. And then what tends to happen is the lighter object is kind of expendable, and it gets kicked out, and we'll see that on its next encounter. So there's the white dwarf has been ejected, and we're left with an eccentric pulsar and white dwarf. We published this in Science just earlier this year. So, in conclusion, modern observatories are creating these wonderful insights into Einstein's universe. Here's all of my people that have helped me, and we're hoping to have more public lectures, and I'd encourage you to come along to them. We're also looking at school holiday programs, school visits, research opportunities for bright high school kids. If you want to do work experience, you can go to astral.institute, fill out the form, or there's a limited capacity. And if you wanted to support our public lecture series, you can click on this QR code and get to a place where any donations will be used to promote our public lectures and hopefully promote STEM in Science Week. Again, thank you.
So we have, I wish we had an intense gravitational field so we could have a bit of a time dilation and let these next 10-ish minutes looking at security stretch. Particularly younger students, think about your questions, there are freebies. I'm going to kick us off Matthew, you mentioned LIGO in passing. What have we, through LIGO, through Virgo, the detection of gravitational waves, discovered about pulsars, about black holes that you've not shared yet? Get to the event horizon and the cool things.
Yeah, so what we've discovered is that black holes actually are much easier to discover merging than neutron stars. But until we built LIGO, you couldn't see any light from black hole pairs, so we didn't know they existed. Unfortunately, there's about 150 black holes merging for every one neutron star pair we can see. There's not a lot for our optical astronomers to do, but we are learning a lot about the fact that there's black holes between like 5 and 100 times the mass of the Sun merging about every couple of minutes in our universe, and we see maybe 1% of it.
Okay, I love this idea. A couple minutes. Is this a question? Yes? Oh, wonderful. Okay, great.
We have a question from the young scientist. Just a section. Okay, I'll say it, but she wondered, how do stars get their names?
How do stars get their names? So if they're close enough, then people in ancient times name them. Different cultures have different names for different stars, but astronomers are not really allowed to name stars after themselves. So they tend to have very boring names like HD 048864. Pulsars are named after where they are in the sky.
All right. Or a very rich patron who built the telescope. So if you donate to Matthew's link, you never know. Yes, okay.
Why the big sun is blue?
Oh, why is the big sun blue? It turns out that when you make gas very, very hot, it goes from red to blue. And the hotter it is, the bluer you are. Cool stars are red, and very hot stars are blue. And the reason it's so blue is because it's very hot. That was a great question.
Very nice and deserved prize. Okay, continuing on. Right at the back, please. Red jacket, there's the microphone for you.
What is the density of black holes?
So black holes have something called the event horizon. And the event horizon is an object that if you cross the event horizon, you leave our universe and go to a different one. So we tend to measure the density of black holes by how heavy they are, divided by 4/3 pi times the event horizon cubed. The density we think right at the center is infinite, but the sort of average density is it's about the same as a neutron star, actually, the smallest one. And then as they get bigger, paradoxically, they get less dense.
Okay. All right. So, could you just spend a little bit that's pretty mind-blowing. Could you just spend an extra minute on the bigger the black hole, paradoxically, the lower its density can actually be lower density than water?
I have an equation. Where was it? Oh, no.
I don't think that's as satisfying an answer as you think it is, by the way.
Yeah, the radius of the black hole depends on this formula, and the radius depends on the mass, but the volume depends on the radius cubed. So as it gets bigger, paradoxically, it gets less dense, because it's mass, radius divided by radius cubed is 1 on radius squared.
You're nodding. I accept that as an answer. Yeah, you're very happy. All right. And then maybe final question in red.
How will the solar system end?
Luckily, the solar system has a very long time left. So it'll probably live for about another 5,000 million years, which is enough for me to stop worrying about it. At the end, it'll run out of hydrogen in the core, and the core will collapse, and the sun will become what's called a red giant. And the red giant will swell up to envelop the Earth, sadly. It's a bit of a sad note to end on. The good news is it's not for a very long time.
We'll be elsewhere. We have traveled the stars. We have the Space Technology Industry Institute at Swinburne. Don't worry, we'll build rockets. We'll have got ourselves out of here. Ladies and gentlemen, that is all we have time for this evening. Enjoy your National Science Week. Please come to our events. And please give a very rapturous round of applause for Professor Matthew Hale.